pipeline runs at 0300 hours. A terminal window on a Ukrainian military analyst's screen. A map overlaid with concentric circles. At the center, the Saratov refinery complex, 780 kilometers from the nearest Ukrainian-controlled territory. A primary atmospheric distillation column. Capacity 14 million tons of crude per year. At full output, it produces roughly $500 million worth of diesel and aviation fuel every 12 months. The drone heading for it cost approximately $70,000 to build and launch. Its guidance system is inertial plus GPS. Its warhead weighs 100 kilograms. It has been flying for 6 hours. And at terminal phase, it will make its own final targeting decision using an AI optical guidance module, without a radio link that could be jammed. This is not a scene from a future war. This is Ukraine in 2026. And the economics of what you just heard are the story. A single hit on an atmospheric distillation column doesn't just damage a building, it disables a refinery for months. The repair cost, between $50 million and $500 million. The disruption, the diesel that never gets refined, the aviation fuel that never reaches Russian airfields, cascades outward for years. And Ukraine is doing this systematically. By May 2026, according to Ukrainian military sources and corroborating open-source analysis, Ukraine's long-range drone campaign had knocked offline approximately 83 million tons per year of Russian oil refining capacity, roughly 25% of the national total. One caveat up front, because it matters. That figure is capacity taken offline, not actual output lost. Russia runs with a large cushion of idle and spare refining capacity it can restart. So the real drop in refined fuel production is smaller than that headline percentage. But even the real drop bit hard. Russian diesel output fell from 7.5 million tons per month to 5.9 million tons per month. Fuel queues formed outside gas stations in Russian cities for the first time in years. The cost-exchange ratio on the most successful individual strikes, 1 to 1,000, or higher. Sit with that number for a second. $1 spent by Ukraine, $1,000 in damage to Russian infrastructure. No weapon system in the history of conventional warfare has produced economics like this at scale, sustained over months, against a peer military with continental air defenses. The question every defense analyst is now asking isn't whether this campaign is working. The open-source data answers that. The harder questions are, how does Ukraine sustain targeting accuracy against hardened, defended, and now dispersed infrastructure? How does Russia adapt its air defenses to cover more than 300 refining facilities? And what happens to the cost math when Russian countermeasures improve? To understand those questions, we need to start with the hardware and the math. If you want to follow every development in this campaign as it unfolds, hit subscribe. We break down these systems as the open-source data comes in. The drone at the center of Ukraine's deep strike campaign is not the FPV quadcopter that became familiar in earlier phases of the war. This is a different class of system entirely. Ukraine's jet-powered long-range strike drones in the UAV-290 class, first revealed publicly at Eurosatory 2026, carry a 100-kilogram warhead, achieve speeds up to 800 kilometers per hour, and operate at ranges up to 650 kilometers. They use inertial navigation systems combined with GPS guidance. They can execute autonomous terminal phase flight, meaning the final approach to target runs without a radio link that could be jammed or spoofed. The UAV-290's all-up weight is approximately 350 kilograms. It launches from a solid fuel booster, then transitions to turbojet cruise. This is not a modified commercial aircraft or an improvised airframe. It is a dedicated military system built from the ground up for standoff precision strike, comparable in concept to a miniaturized cruise missile, but manufacturable at a fraction of the cost of Western equivalents. Cost estimate for systems in this class, based on available procurement and production data, between $50,000 and $150,000 per unit. That range matters because the infrastructure they are targeting costs between $50 million and $500 million per facility. An economic disruption from a single successful strike can reach multiples of that figure when lost production is factored across months. At the conservative end, a $150,000 drone hitting a $50 million processing unit, the ratio is 333 to 1. At the favorable end, a $50,000 drone triggering $500 million in combined damage and production disruption, the ratio exceeds 10,000 to 1. The average across confirmed strikes in the campaign, according to open-source analysts who have tracked Ukrainian targeting patterns since 2024, is estimated at approximately 1 to 100. $1 spent, $100 destroyed. That is the figure Ukraine's military sources have cited publicly, and it is the most efficient destruction per dollar ratio of any weapon system in active operational use anywhere in the world right now. If these numbers are new to you, hit the like button. It helps this analysis reach people who track this conflict. And stay through the second half of this video, because the AI guidance story changes the math in ways that historical comparisons can't fully capture. Now, here is what makes the targeting doctrine as significant as the hardware. Ukraine's long-range drone campaign is not a series of opportunistic strikes against whatever appears in range. It is a centrally directed strategic program of systematic infrastructure destruction. Ukrainian commanders have confirmed this publicly. The 14th Separate Drone Regiment, which manages a core portion of Ukraine's long-range strike operations, operates under monthly directives from the General Staff. Priority nodes are identified at the strategic level. Specific process units within refineries, hydrocracking units, compressor stations, diesel blending facilities, rather than entire facilities. Operators, in the words of Ukrainian military sources, never choose targets independently. I spent time going through open-source analysis of Ukrainian targeting patterns across the past 18 months, and one detail kept emerging: the precision of which units within a refinery were targeted, and how systematically Ukraine worked through the most production-critical components first. This is not random. This is an engineering campaign against an industrial system. The goal is not to destroy buildings. It is to disable specific process stages that cannot be easily bypassed or rebuilt. That distinction explains the 83 million-ton disruption figure. A refinery hit on its administrative building is an inconvenience. A refinery hit on its atmospheric distillation column is a shutdown. Ukraine has been targeting the distillation columns. Russia's air defense network is extensive. The S-400 system, deployed in depth around strategic facilities, can engage targets at ranges up to 400 kilometers at altitude. Shorter-range Pantsir S-1 and Buk-M3 systems have been layered around high-value installations. On paper, a refinery with layered air defense coverage should be difficult to strike. And yet the strikes kept landing. The answer is geometry and volume. Russia has over 300 significant oil and gas processing facilities spread across a country spanning 11 time zones. A realistic S-400 battery covers a protection radius of perhaps 40 kilometers against low-altitude targets, and that radius shrinks significantly when the target is a jet-powered drone traveling at 800 kilometers per hour at low altitude with a small radar cross-section. To protect every secondary refinery in Russia's interior would require hundreds of additional batteries, tens of thousands of interceptor missiles, and operators to staff every position simultaneously. Russia doesn't have that surplus, not while also maintaining air defense coverage for frontline positions. Major cities, the Black Sea Fleet, and industrial centers unrelated to oil. Ukraine identified this gap systematically. The campaign didn't attack Moscow's defended perimeter. It went to Saratov, to Ryazan, to Tuapse, to refineries in Russia's interior that are critical to production volume but not sufficiently protected by available air defense inventory. What's most surprising about this campaign isn't the technical sophistication of the drones. It's the targeting intelligence infrastructure behind them. For each strike to hit the right process unit within a complex industrial facility, Ukraine needed detailed engineering data. The layout of the facility, which column is which compressor station connects to which output. Open-source satellite imagery provides part of that picture. Signals intelligence and human networks provide the rest. The quality of Ukraine's industrial targeting intelligence for facilities hundreds of kilometers inside Russian territory represents a capability that was not publicly understood 2 years ago. By late 2025, the strategic effects were measurable. Russian diesel output fell to levels not seen in years. Russian military logistics, already strained by the consumption volume on multiple front axes, began competing directly with civilian demand. Moscow redirected civilian refinery output toward military needs. The civilians felt it at the pump. The military felt it at the forward supply depot. The second-order effect matters as much as the first. Russian combat aviation is fuel-intensive. A Su-35 in a combat sortie burns thousands of liters per hour. A helicopter assault operation, a consistent feature of Russian offensive actions throughout this conflict, requires fuel pre-positioned at forward airfields. Tightening aviation fuel supply doesn't ground the Russian Air Force overnight, but it constrains sortie rates, limits the depth of strike packages, and forces commanders to choose between missions that previously could all be flown simultaneously. The drone campaign was working at strategic scale, and then Russia made a move that complicated everything. In the final months of 2025, Russian air defense crews began deploying a counter-tactic that open-source analysts had not fully anticipated. Pre-positioning of Pantsir S-1 systems, not around the refineries themselves, but along likely approach corridors, using terrain masking and road-mobile positioning to create unpredictable intercept envelopes. A fixed battery is easy to route around. A battery that can be anywhere along a 200-kilometer approach lane is a different problem. The success rate of Ukrainian deep strike drones dropped. Not catastrophically, overall campaign success rates are estimated at approximately 20 to 30% of sorties resulting in significant damage, but enough to require adaptation. What the coverage largely missed, Ukraine's response to Russian corridor defense wasn't to push through the same approach lanes. It was to identify new target sets in different geographic corridors and to accelerate the AI guidance fielding program that would make GPS spoofing, Russia's other major countermeasure, irrelevant. The GPS spoofing problem had emerged as a serious challenge in late 2025. Russian electronic warfare crews had become sophisticated enough at spoofing GPS signals around high-value targets that several strikes went off course in the final kilometers. The drone reached the target area, hundreds of kilometers of flight completed successfully, and then false GPS coordinates sent the terminal approach to a field kilometers from the intended facility. That gap, when Russia's GPS spoofing was degrading strike accuracy and Ukraine's optical guidance wasn't yet fielded, produced a measurable lull in successful strikes against Tier 1 targets. The lull lasted approximately 2 months. Ukraine's engineers had the answer already in development: AI-driven optical terminal guidance. Instead of trusting GPS in the final kilometers, the drone's last approach is handled by an onboard optical sensor paired with AI pattern recognition that identifies the specific aim point on an industrial structure. The facility is visible. The target unit is identifiable. The guidance locks on to what it sees, not what GPS claims is there. Machine vision guidance like this, the kind Ukrainian firms such as the Fourth Law first proved out on FPV drones, makes jamming and spoofing largely irrelevant in the seconds that matter most. By early 2026, optically guided systems were operational against the same target sets. The accuracy data came back in line with earlier in the campaign. The reported gain from AI optical guidance, roughly 2 to 4 times higher hit probability compared with GPS-only terminal guidance. If baseline GPS accuracy puts a warhead within 20 meters of the aim point, the better end of that range means hitting within about 5 meters. For a 100-kilogram warhead aimed at an atmospheric distillation column, the difference between 20 meters and 5 meters is the difference between damaging the facility and disabling the specific unit that takes months to replace. Here is the central question at the halfway point of this analysis. One the defense community has not reached consensus on: is Ukraine's deep strike campaign a war-winning strategic instrument or an attrition tool whose full effects will only be visible years from now? Put yourself in the position of a Russian logistics officer at a forward supply base in Zaporizhia Oblast in June 2026. You've received word that your next diesel allocation has been cut by 15%. The armored unit you're supporting is scheduled for an operational push in 6 days. You have to choose which vehicles get fuel, which convoys get delayed, and whether to flag the shortfall up the chain or make do with what's available. That is what Ukraine's drone campaign is actually producing. Not a clean, visible collapse, but a slow compression of options across the Russian logistics system. The question is whether that compression reaches a threshold of operational failure before Russia adapts its production system, finds alternative supply, or implements some other workaround. And the honest, analytical answer is, we don't know yet. What we do know is that Russia has attempted multiple adaptations. It has dispersed refining operations across smaller, harder-to-target facilities. It has invested in hardening some installations. It has imported refined products where domestic production fell short. None of these adaptations have fully offset the production losses. The open-source data on export flows and domestic fuel pricing makes that clear. But Russia has not reached a fuel crisis that triggered military collapse. The campaign is creating real pain. It has not yet created a decisive break. That gap is where strategic bombing campaigns historically live. The history is worth being honest about. Strategic bombing has a mixed record. It disrupted German industrial production in the Second World War, but German war production actually increased until 1944, 2 years after the bombing campaign began. The mechanisms of industrial adaptation are powerful. Targeting refineries specifically, as opposed to ball-bearing factories or rail networks, is historically among the more effective approaches because fuel cannot be easily substituted and production losses compound over time. Here's the take that may get pushback. Most coverage of Ukraine's drone campaign understates how long it will take to see decisive effects and overstates the immediacy of the fuel crisis because short-term output drops make compelling statistics. The 1-to-100 cost ratio is real. The 25% disruption of refining capacity is real, but strategic effects of this kind compound over quarters and years, not weeks. Any analysis that frames this as a near-term war winner should carry that caveat clearly. The campaign is strategically significant. It is not a knockout punch. It is a slowly tightening constraint. Now, the AI layer changes the math in ways that historical strategic bombing comparisons cannot fully capture. There's a question worth debating in the comments. The AI guidance module, at terminal phase, identifies its own aim point through pattern recognition, without a human guiding the final approach. A human approved the mission. A human chose the target facility. But the specific impact point is determined by the algorithm. Does that cross a meaningful line in what we call autonomous lethal systems? The drone is making the final aiming decision independently. Ukraine's position is pragmatic. Optical guidance improves accuracy and reduces civilian collateral risk by ensuring the warhead lands on the intended industrial component, rather than an adjacent structure. Russia's intercept systems don't distinguish between human-guided and AI-guided terminal approach. But the principle, removing human control at the final decision moment, is one that every major military is now formally studying. Comment below. We read everything. The broader doctrinal implication is this. If Ukraine can field AI-guided terminal guidance on a $70,000 airframe, manufactured at scale under wartime conditions, what does that mean for the military balance between states that invest heavily in expensive platforms and states that invest in cheap, AI-enhanced autonomous systems? The Ukraine conflict is answering that question operationally, not theoretically. The cheap autonomous system achieves precision effects that previously required expensive precision weapons. The Tomahawk cruise missile, which costs approximately $2 million per unit, achieved reputation-defining accuracy in the 1990s. Ukraine's AI-guided strike drone is approaching comparable terminal accuracy at approximately 3 to 4% of the cost. That ratio will not stay at 3%. As AI guidance systems improve and manufacturing scales, the cost of achieving precision effects continues to fall. The infrastructure being targeted does not become cheaper to protect or repair. The defense procurement implications are active now, not theoretical. Multiple NATO member states have dispatched delegations to study Ukraine's drone production and AI integration program over the past 12 months. The Brave One AI Military Development Data Room, Ukraine's civil military innovation hub that has accelerated development cycles by removing conventional procurement bureaucracy, has received interest from partner militaries studying how to replicate the institutional model. One detail that stayed with me going through reporting on Brave One, the program's operational philosophy is explicitly structured around 30 to 90-day development cycles from concept to field testing. That timeline does not exist in any NATO procurement framework. A comparable guidance module enhancement for a U.S. cruise missile would require years of development testing, safety certification, and acquisition process steps, because the system operates inside a peacetime regulatory architecture designed to prevent failures of a different kind. Ukraine is operating inside a wartime architecture that accepts faster failure cycles in exchange for faster capability delivery. The lesson is institutional as much as technical. Ukraine built an AI-guided precision strike capability in wartime faster than any Western nation would have in peacetime. NATO is now studying whether any element of that institutional model is transferable, and what would have to change in peacetime procurement culture to allow it. Ukraine had the GPS spoofing problem solved. The AI guidance was fielding. And then, in May 2026, came a development that changed the scale of what both sides were dealing with simultaneously. Russia fired 8,150 Shahed-type drones in a single month. Record volume. Simultaneously, it escalated ballistic missile strikes on Ukrainian energy infrastructure. Ukraine's air defense network intercepted approximately 90% of those drones, a figure that sounds like a success until you look at what 10% of 8,150 means. That is more than 800 drone impacts in a single month. Ukraine's catapult-launched interceptor drones, a class of autonomous counter-drone platform deployed specifically against Shahed-136 targets, are one layer of the response. They engage incoming drones autonomously, without a human managing each individual intercept, at a fraction of the cost of a surface-to-air missile. The system applies the same AI autonomy logic to defense. When incoming volume exceeds the capacity of human-managed interceptors, you need systems that can engage at the same scale. The economics of intercept matter here. Western missile interceptors, Patriot, Iris-T, NASAMS, cost between $1 million and $4 million per shot. If Russia fires $20,000 Shaheds and forces $4 million interceptor responses, Russia wins the exchange economically, even when Ukraine stops every drone. Autonomous counter-drone systems costing tens of thousands of dollars per interception, not millions, are the only way to correct that math at volume. Ukraine is building them. NATO is analyzing the operational data. The cost exchange dilemma runs in both directions simultaneously. Ukraine is generating favorable ratios on offense with its deep strike campaign. Russia is generating pressure on defense costs with its Shahed volume strategy. The side that solves autonomous counter-drone economics first gains a structural advantage that compounds over months. What makes this phase of the conflict notable when viewed as a whole? This is the first time in the history of strategic air campaigns that a non-great power is conducting precision industrial targeting against a nuclear-armed state, using AI-guided autonomous systems costing tens of thousands of dollars, built under wartime conditions with civil-military development timelines measured in months. The strategic bombing campaigns of the 20th century were conducted by large, expensive air forces against nations without equivalent strike-back capability. What Ukraine is doing is categorically different. The lessons it is generating on cost ratios, on the relationship between AI autonomy and targeting precision, on wartime institutional innovation, will drive defense procurement debates for the next 2 decades. That is the stated assessment of multiple NATO planning staffs. The fuel crisis in Russia is documented. The adaptation story is ongoing. And the next phase of Ukraine's campaign has already been publicly signaled, in a direction that extends well beyond refineries. At Eurosatory 2026, Ukraine's Ukroboronprom presented 2 systems that expand the strike portfolio in significant ways. The Sea Trident is a naval and submarine-capable drone system. In the context of Black Sea operations, where Ukraine's surface naval drones have already destroyed or damaged a substantial fraction of Russia's Black Sea fleet, forcing it to withdraw from Sevastopol, a submarine-capable variant changes the threat calculation for Russian naval assets in ways that surface drones alone cannot. A surface drone can be detected by radar. A submarine-capable drone operating below the surface has a different detection signature and a different intercept problem. Russia's naval anti-submarine capabilities in the Black Sea have not been exercised against small, fast autonomous underwater vehicles in large numbers. This is an untested pairing of threat and defense. And at the same show, Ukraine displayed the other side of the equation. The Dragon system is a ground-based air defense launcher that fires repurposed air-to-air missiles, R-73s and Sidewinders, to knock down incoming Shahed drones at a fraction of the cost of a Western interceptor. It is the defensive mirror of the offensive cost math, a cheap system built to break Russia's Shahed volume economics. Deep strike drones on offense, improvised interceptors on defense. Ukraine is attacking the cost exchange problem from both ends at once. And that combination of diverse, cheap, purpose-built systems, rather than any single dominant platform, is exactly how a numerically inferior force outlasts a layered air defense architecture. Every major military watching this conflict is now rethinking its own vulnerability to a sustained, affordable, AI-guided deep strike campaign against industrial and energy infrastructure. The question is no longer whether cheap, long-range drones can threaten peer military infrastructure. Ukraine answered that across 2025 and 2026. The question is how to build defenses against a threat that becomes cheaper, more accurate, and more autonomous every 6 months. When the cost curve for the threat runs downward, while the cost curve for comprehensive defense runs upward. One element of this campaign we couldn't fully verify from open-source reporting: the precise breakdown of how Ukraine's industrial targeting intelligence for deep interior Russian facilities is sourced, signals collection versus human networks versus partner nation support. The answer matters because it determines whether the campaign model is replicable by other states without Ukraine's specific partner relationships. If you've seen analysis on that breakdown, or work in a field adjacent to it, drop something in the comments. It's a genuine gap in the open-source picture. There is no clean conclusion to this campaign because it is still running. Every week, Ukrainian deep strike drones are flying toward Russian refinery targets. Every week, Russia is adjusting its intercept posture, dispersing refining capacity, and importing refined products from partners willing to trade under sanctions pressure. The 83 million ton disruption figure is the current state as of May 2026. What it looks like by the end of 2026 depends on variables: Ukrainian production rates, AI guidance accuracy improvements, Russian defensive adaptation, third-party fuel supply chains that are genuinely uncertain. Honest analysis doesn't resolve those variables. It maps them. Here's what is not uncertain. The cost-exchange ratio isn't improving for Russia. The drones get cheaper as Ukrainian production scales. The AI guidance systems become more accurate as algorithms train on operational data. The target set expands as new systems come online. The direction of the trend is clear, even if the destination and timeline are not. Most people assume that air defense technology will eventually close this window, that Russia will build a system dense enough to protect its refinery network, and the campaign will run out of viable targets. The evidence from the past 18 months tells a different story. Russia has tried exactly that approach with its Pantsir corridor deployments, its GPS spoofing expansion, its intercept volume campaign. Each adaptation produced a Ukrainian counter-adaptation within months. The cycle runs faster than a conventional air defense procurement cycle. One final number: Ukraine's FPV drone production reached over 100,000 units per month by early 2026. Long-range strike drone production operates at smaller scale. The economics and engineering complexity are different, but the same industrial mobilization logic applies. Ukraine has built a wartime defense industry from near zero in 4 years. The systems coming out of it are competitive, cost-optimized, and increasingly AI-integrated. That capability is what a $70,000 drone is sitting on top of when it flies toward a refinery in Saratov. The refineries don't get cheaper to protect. The drones don't get more expensive to build. The math runs in only one direction. Subscribe. We break down every major development in this conflict and in modern military technology as the open-source picture develops. The next video covers Ukraine's naval drone campaign in the Black Sea, the specific operations, the systems, and how a country without a functional blue water navy forced Russia's Black Sea fleet out of its home port. That story has the same cost ratio logic, and it ended with consequences that nobody in naval doctrine anticipated.